Gates just ventured into this clean energy that will shock Elon Musk. At the Massachusetts Institute of Technology, MIT, a group of scientists has gathered to conduct research on the possible use of nuclear fission energy that can be used for commercial purposes. In contrast to nuclear fission energy, which releases radioactive waste, nuclear fusion energy is 100% clean and has no carbon emissions. This could be a breakthrough for all forms of energy consumption as we know it. Hello, and welcome to Future Tech. In this video, we'll be diving into the details of this marvelous scientific research and its implications for us. If you're interested to find out, then stick around to the end of the video and don't forget to press that big thumbs up button. Alright, let's get right into it. In an effort to make nuclear fusion energy available for commercial use, an MIT spinoff has signed an agreement to conduct its research for the next 5 years. The Plasma Science and Fusion Center, PSFC, at the Massachusetts Institute of Technology, MIT, has joined hands with Commonwealth Fusion System, CFS, in this regard. This collaboration will conduct its research on plasmas, technology, and fusion science in a lab at MIT. This partnership is backed by huge investors including Bill Gates, Jeff Bezos, and fossil energy giants Eni and Equinor, and is believed to be on track to creating the world's first fusion device that will release more energy than is required to power it up. If the research turns out to be successful, it could make nuclear fusion energy available for wide-scale use. While some claim it has the holy grail of clean energy, some others remain skeptical and call it nothing more than a distraction from other proven environmental-friendly technologies such as solar, wind, or hydro. CFS Chief Executive Bob Mumgard said in an interview that fusion could play a vital role in the energy transition by filling the gaps left by wind and solar. You might be wondering though, why are scientists and researchers not working on fission reactions instead, in which atoms split apart, and why are they so eager on separating these two cousin technologies from each other? Well, that's because nuclear fusion produces no radioactive waste. Nuclear fusion is inexhaustible and has a lower cost. The energy released by nuclear fusion is 2 to 3 times more than that released by fission reactions. No production of greenhouse gas, soot, acid rain, and no possibility of leakage or runaway of harmful materials in fusion reactions. But what is a nuclear fusion reaction? Well, it is the name given to the process in which smaller atoms collide with each other and as a byproduct release atoms with a bigger nucleus as well as large amounts of energy. This process has been occurring in space for as long as we know it, and scientists have been working on recreating it here on Earth to generate energy in a carbon-free manner. There's a catch though, because as a requirement for this process to function, it requires temperatures way higher than any solid earthly material can withstand. However, there's one solution that scientists are working on in which a strong magnetic field is used to contain the hot plasma soup of protons and electrons. Since these particles are charged, they can be contained using a strong magnetic field. Over the years, the MIT partnership has been trying to build a superconducting magnet that they believe will help in achieving the ignition threshold required for nuclear fusion energy. Basically, a very powerful magnet that requires very little energy. Unlike conventional electromagnets that are made of copper, the CFS's superconducting magnet will be made from rare earth barium copper oxide, REBCO, and according to their claims on the website, it can help make smaller, faster, and less expensive reactors. In an announcement made last year in September, the partnership was successful in creating a magnetic field of 20 Tesla, the most powerful high-temperature magnetic field ever created on Earth with the use of high-temperature superconducting (HTS) magnet technology. This test was conducted at MIT Plasma Science and Fusion Center in Cambridge, Mass. For reference and better understanding, you need to know that 20 Tesla is 12 times more than the magnetic field of a traditional MRI, or magnetic resonance imaging scan. And this is not even the best part. Apparently, this field was generated while consuming only 30 watts of energy. This is almost 1,000,000 times less than the amount of energy required by the traditional copper-conducting magnet that MIT was working on previously, said Dennis White, director of MIT's PSFC and a co-founder of CFS, in a press release. A space-age reactor called the Tokamak Spark, set to be completed in 2025, is used in which the magnets are placed. This device uses a considerable amount of energy in an effort to release more than what's required to power it. Through its spherical or almost donut-shaped body, a stream of plasma moves through, which is contained within the body with the help of a powerful magnetic field generated by the CFS's superconducting magnet. Because the plasma is too hot for a classic instrument or material to contain, the superconducting magnet requires a lot of energy to hold and insulate it in the tokamak designs. Since the magnet operates without any resistance, it can help in cutting down the amount of power used to hold a magnetic field together. In spite of all this, the energy costs to run the Tomahawk are still very high. The reason being that in order for the magnets to operate, they have to be cooled to extremely low temperatures, and this requires a lot of energy. This explains why an effort to make machines such as Tokamak hasn't been successful till now, because of the negative net energy we get from nuclear fusion reactions. Net energy means that the fusion machine releases more energy than it takes to initiate and sustain the reactions, says CFS and MIT's PSFC. Because fusion reactions in space naturally operate under extreme temperature, pressure, speed, etc., we require the same environmental conditions for fusion reactions to be fruitful on Earth. For this reason, no company has ever been able to achieve net energy fusion as of yet. The scientists and engineers working for CFS and PSFC claim that the performance of their new supermagnet technology will be revolutionary and will pave the way for further technological development in this field to commercialize fusion. This magnet will change the trajectory of both fusion science and energy, and we think eventually the world's energy landscape, said White. The MIT and CSF use high-temperature superconductors to build a magnet that would be able to reach a 20 Tesla magnetic field. The scale and performance of this magnet are similar to a non-superconducting magnet that was used in the MIT experiment that concluded its experiments 5 years ago, White said. But the difference in terms of energy consumption is rather stunning. After a successful demonstration of this technology is conducted, CFS aims to build a commercial-scale nuclear fusion reactor that will supply energy to the grid that may even someday power our own homes. According to a statement issued by the International Atomic Energy Agency, IAEA, we can expect that this form of energy will provide us with a limitless, economic, and sustainable alternative while generating minimal radioactive waste. In a press release issued earlier, it was stated that the MIT partnership will work in such a way that the scientists of PSFC will focus on its mission of cutting-edge technology and education, while a CFS will build the Spark, Tokamak, and develop a commercial fusion product. Building 1 or 10 fusion plants doesn't make a difference. We have to build thousands, said Dennis White, PSFC director. The real enemy here is time, and we want to remove as many impediments as possible and commit to funding a new generation of scientific leaders. Those are critically important in a field with as much interdisciplinary integration as fusion. It's to be noted, however, that if successful, the use of superconductor magnet technology will not just be restricted to its use in nuclear fusion reactors. Technological advancements as such can be used to make trains faster, particle accelerators cheaper and bigger, and improve nuclear imaging. The limit is our imagination, really. In February this year, a spin-off from Oxford University revealed their own version of a nuclear fusion reactor that doesn't rely on magnets or laser, a marvel that they want to make available as a commercial-scale device by 2030. And this is it for today's video, guys. We hope you enjoyed it, and if you did, then don't forget to subscribe to our channel and share this video with your friends. We would also like to hear your thoughts in the comment section down below. What do you think this beastly magnet can be used for apart from nuclear fusion reactor? And when do you think this technology can be available to us? Do you have any questions for us? Feel free to let us know down below. See you in our next video.